So I want to talk about, as I said, I want to talk about dynamics of rational maps on the Riemann sphere. So by the way, since I'm using the computer as well as the iPad, I believe there will be a little bit of a lag when I write on the iPad. So please stop me if I'm unclear or if you cannot hear me properly. Okay, so let me start the story. So rational dynamics on the Riemann sphere, which I'll denote by C hat, it deals with, let me introduce the object and then I'll say why this is something that's interesting. So as we all know, the Riemann sphere is just the complex plane. Compactified is the one-point compactification. You just add the point at infinity and what you get is a sphere. So that's, everyone is familiar with that. The next thing we know is that the Mobius maps, which are maps of the form AZ plus B over CZ plus D, where AD minus BC is not equal to 0. These are so-called automorphisms of the Riemann sphere. So that means these are conformal automorphisms. In other words, these are holomorphic maps from the Riemann sphere to itself, and the inverse of them is the inverse of such a Mobius map is also a holomorphic map. That's what conformal automorphisms mean. And in today's talk, we are going to look at rational maps on C hat, which are essentially all possible holomorphic maps from the Riemann sphere to itself. This is something that we see when we do maybe a first course in complex analysis or a second course in complex analysis, that any holomorphic map from the Riemann sphere to itself is of the form Pz over Qz, where P and Q are polynomials. Okay, so that's the object that we are going to look at. And we are going to be interested in the iteration theory of rational maps. So we are going to take a rational map on the Riemann sphere and we are going to iterate the map on the Riemann sphere and understand the dynamics. So what does this all mean? This fits into the broader paradigm of dynamical systems. So since I'm not going to assume familiarity with anything much beyond maybe basic, maybe beyond undergraduate stuff. So a dynamical system is a space X, which is just a set rather. And a map, for us, a dynamical system is this. There are more general definitions of dynamical systems, but this is going to be enough for today's talk. I have a set X and I have a map F acting on the set, takes the set to itself. So that's important. Here, F is not a map from X to Y, it's a self map of X. Now, once you have such a thing, you can look at the second iterate of the map, which is simply the composition F compose F. And we write it F squared. And we can also, since X always goes to X, if you start with an arbitrary point in the set X, suppose here's a point P, when you apply the map F, it goes somewhere to FP. And then since f of p is also inside of the set X, you can apply the map F again, and you're going to go to some point which is called F square of P and so on. And the fact that F is a self map implies that you can carry on this procedure. You can keep applying the iterates of the map F on the point P infinitely many times. So understanding, so this is what dynamics means. So f to the n is defined as the n-fold iterate of the function f. So what are some stuffs, what are the questions that one wants to understand about the iteration theory of a map? And why am I calling it dynamics? I'm calling it dynamics because I'm thinking of the map F as a rule that changes the state of the space X. So you have a space X, you have points there, and the set changes. The points move under the action of the set F. That's why it's called dynamics. So it's an evolution of a set. Typical questions that one wants to understand are the following. What do orbits look like? Where the orbit of a point X is the following. You start with the point X, or maybe P, because I'm using P here. The orbit of a point P is just the sequence P, comma f of P, comma f of P, and so on. So you start with an arbitrary point, and you keep applying the map F on the point P, and you get a sequence, and you ask, what does the sequence do? Does it have a limit? Does it have accumulation points? Does it escape to infinity in some sense? Or does it converge to some point which is an attracting fixed point? And if you understand the orbit of the point P, then you want to know what happens for nearby points, if you can make sense of the word nearby. So to meaningfully ask some of these questions, it's not a good idea to just work with the set X. Rather, it makes more sense to put some structure on the set X. What does that mean? You want to at least have a notion of topology on the set X, because to understand the behavior of a sequence, you need to make sense of convergence, accumulation, and so on. So at least you need to have open sets to make sense of these things. That's why we at least want the space X to be a topological space, and I want my map F to be a continuous map. So these are called topological dynamical systems. More precisely, one really wants this to be a metric space. Things are much easier when you have a metric structure. We all know from basic courses in topology that if a space is non-metrizable, then some things can be pathological and so on. So to keep things nice, we want to have a metric space X and a continuous map acting from X to itself, and then we want to understand the orbits of such a map. That's sort of the general goal of discrete dynamical systems. Now, of course, it's beyond the scope of this talk to mention all the different directions in dynamical systems, but let me at least say that once you understand some properties of iteration of continuous maps on metric spaces, you want to put more structures on it, and you want to see how these structures interact with structures of orbits. In that direction, it is natural to look at or to try to upgrade a topological dynamical system to, say, a smooth dynamical system, where a smooth dynamical system is one where the space X is not just a topological space, but it also has some sort of differentiability structure. So you can think of it as Rn, or if you have more familiarity with smooth manifolds, you can take X to be a smooth manifold. And in that category, you will take your function f to be a differentiable map of a smooth manifold. And then you want to understand the dynamics of a differentiable map on a smooth manifold. One could also do it in a slightly loose category of measurable dynamics, but let me not say anything about that. Now, beyond smooth dynamical systems, so again, what is better than smooth? Well, there's real analytic, and then there is complex analytic, or holomorphic dynamical system. These are, at least so far as the maps are concerned, holomorphic maps are quite nice, they're well understood and so on. So maybe the hope is that if I have a holomorphic dynamical system, which means that I have, I'll write this, but I'll not work in this generality. I have a complex manifold X, and my F is a holomorphic map or meromorphic map of the complex manifold X. And then you want to understand the iteration theory, or in other words, structure of orbits of F. So that's the general introduction to dynamical systems, or holomorphic dynamical systems. But in today's talk, we are going to highly specialize the situation. Instead of looking at arbitrary complex manifolds, we are going to look at complex one-dimensional manifolds or Riemann surfaces. If you know what these things are, great. If you do not, don't bother. I'm not going to work in the generality of all Riemann surfaces. I'm going to work with the simplest possible compact Riemann surface. And again, if you don't know what a Riemann surface means, here is what I really care about. I really care about the Riemann sphere. So in this context, what we were going to look at, these rational maps on Riemann spheres, that's precisely for holomorphic dynamical systems on one-dimensional complex manifolds. One wants to understand the iteration of holomorphic maps of Riemann surfaces. And in the case of the Riemann sphere, since the holomorphic maps are precisely the rational maps, we are going to be interested in understanding dynamics of rational maps on C hat. Let me also mention that dynamics of Mobius maps is also interesting, but one needs to look at or work with a group of Mobius maps. If you want to understand the dynamics of a single Mobius map on the Riemann sphere, that gives you highly uninteresting dynamics. I'll not get there, but the idea is that if you start with a single Mobius map, keep iterating it on the Riemann sphere, all points will diverge to something or converge to something. So the dynamics is quite uninteresting there. In order to have some interesting dynamics, we want our rational maps to have degree at least 2. Now, what is the degree of a rational map? The degree of a rational map is simply, so if I call this R, if a rational map R is the ratio of two polynomials P and Q, then the degree of R is the topological degree, is the generic preimages, is the number of generic preimages. So it's just the max of the degree of P and the degree of Q. Yeah, so you look at the degree of the two polynomials, the larger one is called the degree of the rational map R. And why is this called degree? Because, well, I mean, if you want to compute the number of preimages of a generic point, you solve the equation Rz equals W, let's say, and you see that essentially after clearing denominators, you are solving a polynomial of degree R, so you're going to get degree of R many preimages. So that's why the word degree makes sense. Okay, so we're going to look at rational maps of degree at least 2 on the Riemann sphere. We're going to iterate them, and we're going to understand how orbits look like. So now, in this particular case, what are the natural questions to ask? Before I introduce that, here is a word on motivation. So how did this theory really come into play, or how did it come into existence rather? So the history goes back like this. In the 1920s, two French mathematicians, Pierre Fatou and Julia, they started looking at iterations of holomorphic maps, not just rational maps. They also looked at iterations of transcendental. So yeah, so something that I'm not going to talk about today, but one could. Instead of looking at the Riemann surface, Riemann sphere, one could just look at the complex plane. And we know the holomorphic maps on the complex plane are just entire functions, like the exponential and so on. One could also study the dynamics of entire transcendental maps on the Riemanns, on the complex plane. But that's a somewhat different direction so far as the results go. So I'm not going to pursue that direction today. Okay, so these two mathematicians, Fatou and Julia, they started studying the basic dynamical properties of rational maps, sort of founders of rational dynamics. Then there was a long period of inactivity somehow. In this field. This was around the First World War, and then after the First World War, there was, of course, some of their results were kind of forgotten or went out of context. So, by the way, this Fatou is exactly the same Fatou as the Fatou's lemma from measure theory. And the reason why he proved Fatou's lemma from measure theory was to prove some facts about rational dynamics. So this long period of inactivity was approximately from the 1930s to 1960s, except a few results, except some important contributions by I should mention Kremer, Siegel, Brolin, and so on. But let me not get in this direction. I don't want to give a comprehensive introduction. Then somehow the whole subject kind of resurfaced in 1980s, and partly because of two reasons. The main reason is that people started looking at pictures of rational dynamics, and I'll make that precise. What do I mean by the picture of a rational dynamical system? But whatever this means, as you can see, I have a picture of a rational dynamical system here. And I'll try to explain what this means in a little bit. But before I give you the definitions, the point is these are pictures that are drawn by, in principle, iterating the function R infinitely many times, because you want to understand the orbit of a map, orbit of points under a rational map. So you want to iterate a given point infinitely many times. So, drawing the pictures by hand doesn't make any sense, because you cannot try to track the orbit of a point under infinite iterations. Well, then you ask, well, maybe infinite is too much. Even a computer cannot. Maybe a computer can do 50,000. So maybe 50,000 is good enough. That's what people started thinking. Maybe what if I tell a computer to iterate points and color them based on different behaviors of orbits? Will the computer be drawing something that's a faithful representation of the actual dynamical plane? And it turns out that this is true in many cases. In particular, it's true in this particular case. Now, what is this? Oh, so just to continue what I was saying, so the reason why there was this reinvention of the subject of some sort in the 1980s was that people started having computers. Before that, there were no computers. People couldn't draw pictures. Once they had computers, they managed to draw pictures. And one of the persons was sort of the who was one of the big proponents of this kind of ideas was Benoit Mandelbrot. So Mandelbrot was a mathematician, dreamer of some sorts in IBM, and he had access to good computers at the time. So he drew pictures of what is called the Mandelbrot set these days. which is this object here, and I'll try to come to it towards the end of this talk. This is what is called the Mandelbrot set. Now, this is such an intricate object that it's impossible to study it if you have never seen a picture. It's almost impossible to even come up with good conjectures. Okay, so to be a little more precise mathematically, let me try to explain what we are trying to draw in this particular picture. Okay, so here's what we are trying to draw. Suppose you have a degree d polynomial. And you want to solve the roots of the polynomial. Now, something that we teach undergrads in maybe numerical analysis or something, there's this so-called Newton's method that allows you to solve for the roots of a polynomial, which entails pick a starting point So my goal is find roots of f. And to do so, one starts with some kind of a starting point and then iterate a function n of f. Let me do it in the real line for now. That's given by x minus f prime of x over f of x. Now, if you remember some basic stuff from undergrad, Newton's method or numerical analysis, or if you haven't seen this, these are very easy things to check. So it turns out that if I have a root at some point, if I am looking at a root of a polynomial f, clearly that is going to be a fixed point of the function nf, right? So if f of p is equal to p, then, and if and only if nf of p, if f of p is equal to 0, just give me a moment. I messed up. My sign is wrong here. Okay. Yeah, so if f of p is equal to 0, then clearly nf of p is equal to p. So finding the roots of the polynomial p, of the polynomial f, is equivalent to finding the fixed points of the Newton map n of f. And finding the fixed point is a tricky question. It really requires, so what we tell students to do typically, that we do a few things. If we give them a real function, sometimes we give them a base point or a starting point, and we tell them to iterate the Newton map nf so that it converges to a fixed point. So that means the fixed point is maybe attracting in some sense. So it attracts the forward orbits of nearby points. Or we tell students to come up with a good starting point. Now, in real analysis, you can do this because you have the intermediate value theorem. So sometimes you know that there is a root between this number and that number that gives you a judicious choice of a starting point. What about complex polynomials? We know that not all roots of a complex polynomial lie on the real line. So what if I want to find all the complex roots of a polynomial f? I have to find good starting points, and now I do not have my intermediate value theorem. How can I find good starting points for an arbitrary complex polynomial f? So the first observation is that if f is a polynomial, clearly this function n of f, which is written this way, n of f is a rational map. So your search for the roots of the polynomial f translates to the search of the fixed points of the rational map n of f, and fixed points are dynamical objects. Why is a fixed point a dynamical object? Because in order to have a fixed point, you have to have a map from the set to itself, so you can iterate, and the fixed point is given by the fact that you start with the point. In one iteration, the point comes back to itself. So can I have a nice theory of trying to find all the fixed points of a rational map? This question led people to try and understand the general dynamics of rational maps. In particular, when you have, by the way, not every rational map arises as the Newton map of some polynomial, but those particular rational maps that arise as the Newton map of some polynomial are special. And this picture is of one such guy. Now, what do we see here? What we see are the following. You see this point over here, the center of the blue region, and a point over here, the center of the red region, and a point over here, the center of the green region. These 3 points, so I have a cubic polynomial f. These 3 points are the roots of 3 roots. So those are the roots of the cubic polynomial. And what does blue signify? Blue stands for all possible points in the complex plane such that if you start iterating the Newton map at a blue point, let's say here, or even here, or there, then you will eventually converge to this particular fixed point. And red and green are also similar. If you start with an arbitrary red point in the whole complex plane, you will converge here under the Newton map. And if you start with an arbitrary green point, you'll eventually converge there. So these are called the basins of attraction of the 3 fixed points, or the basins of attraction of the roots of the polynomial. And the good news here is that for this particular picture, the union of the basins of attraction of these 3 roots is not quite the whole Riemann sphere, because you can see there are points where these guys intersect. These points are not going to be attracted to any of the roots, but such points form a measure 0 set. So, and we know that the probability of picking a point from a measure 0 set is 0. So with full probability, if you pick a random point from the plane or from the sphere, its forward iterate under the Newton map is going to converge to one of the roots. That's good news. That means, well, you don't have to be too careful in this particular picture. You take a point and with almost certainly its forward orbit is going to converge to one of the roots. You don't know which one, and that's a bit complicated, because if I try to blow up the picture somewhere over here, you'll see that a red and a green and a blue lie very close to each other. So which one you're converging to is hard to say. Okay, but now that leads to the following question. Is this always the case? If I take an arbitrary polynomial f and look at the corresponding Newton map n of f, is it true that the basins of attractions of the roots, meaning the set of points in the whole complex, in the whole Riemann sphere, whose forward orbits are going to converge to one of the roots, is going to be a full measure set, meaning its complement is a 0 measure set in the Riemann sphere? And this was a question by Stephen Smale, who was a Fields medalist, and he was looking at these sort of objects, and it turned out to be false. So that's bad news. Here's a picture. This corresponds to, again, some cubic polynomial. As you can see, there's a root here, root there, and root there. If your starting point is red in color, then you eventually converge here. If you are blue, then you converge there. And if your starting point is green in color, maybe over here, let's say this one, you'll eventually converge there. But we see another color here. There's a black color too, and there are open set of points that are black. What's happening for the black points? So what's happening for the black points is the following. Every black point eventually converges to this particular component, this particular black component, and this is a fixed point. This component is fixed. So if you take any point in this black component and apply the Newton map, you are going to fall in that component. So what does that mean? It means that if you start with any point that is black in color in the whole Riemann sphere, eventually you're going to be sucked up by this point or this particular component over here. So you're not going to converge to any of the roots under the iteration of the Newton map. Therefore, our initial hope that with almost probability with probability equal to 1, we are going to converge to the roots of the polynomials, it turns out to be false. There are indeed open sets of points where points such that if you start with one of these points, you don't converge to any of the roots. So this makes it bad because then you have to work harder, but also exciting. Then you have to ask, then you ask questions like, okay, so how can I possibly find a set of points that will give me all the roots? So if I hand you a general polynomial f, arbitrary polynomial, very high degree, you can compute, you can write down the Newton map n of f given by the formula that I had written earlier. So in complex, it is just z minus f of z over f prime of z. You can always write down the Newton map. The question is, for a given polynomial, how can I come up with a finite set of points, because my computer cannot iterate infinite many points? Can I come up with a finite set of points such that if I iterate my Newton map n of f on these finitely many points, it will eventually give me all the roots? So that obviously will require understanding, or good understanding, of the dynamics of the maps in f. That's one of the major motivations, one of the early motivations to study the dynamics of rational maps. Okay, here are some pictures. Okay, yeah, so these pictures are just, okay, now I have to say a little more. These are not Newton maps anymore. So what am I drawing? Now let's try to, since I'm trying to keep things at some sort of intuitive heuristic level, I'll try to give less proofs. Some definitions are obviously important. So what is a Julia set? So the Julia set, written as the J of a rational map R, is just, let me first define the Fatou set actually. The Fatou set, which is called the F of R, is the largest open set, or open set in C hat, on which the iterates of the rational map R form, the sequence forms an equicontinuous family. Okay, why is this important? Why the word equicontinuous comes in over here? So to just recall what equicontinuity means is the following. Equicontinuity means that you give me an epsilon, so given epsilon positive, there exists delta, such that whenever x, y, 2 points x comma y are so a metric on the Riemann sphere by D, it's not the Euclidean metric, right? So because I can have, my x could be a point at infinity, that's why I'll write D. So such that, so yeah, so just before talking about equicontinuity, so we know that continuity is a statement about a single function. Uniform continuity is a continuity statement for one function in a uniform sense. So uniform continuity for the function R would just be this, right? So we all know that given epsilon, there is a delta such that whenever 2 points at delta close, their images are epsilon close. But equicontinuity is a statement about a family of functions, and it basically says that it's a statement about uniform continuity of all the functions in a uniform way. Meaning, given an epsilon, there is a delta such that whenever 2 points at delta close, then the distance between r to the nx and r to the ny, recall that these are just the n-fold iterates of the points x and y. The distance between these 2 points is at most epsilon for all n. That's the important thing. And the delta does not depend on n. Why is this good? Why is it a desirable property for studying the dynamics? Now, so if I try to unravel the definition, let's try to see what it means. It means that I have my Riemann sphere. Let me just draw it as a large disk. And I have 2 points, x and say y. And I'm looking at the dynamics of the points x and y. So here is r of x, r square of x, etc. This is r to the n of x. And suppose that my points x and y lie in the Fatou set. Right? So suppose that they are so suppose that they are just a second. Okay, so so suppose that I have 2 points. I have chosen 2 points. Here's the, sorry, this is what I want to say. So suppose that x comma y lie in a connected component of f of r. Right, so you take 2 points that lie in the, so I have defined the Fatou set as the largest open set on which the iterates form a form an equicontinuous family, and I take 2 points that lie in the same component of this Fatou set. Then the condition that the 2 points are close imply that their forward iterates r to the nx and r to the ny are also close for all the rough structure of the iterates of x. So meaning if I suppose I know what the orbit of x does, then I also know what the orbit of y does, because if x and y are close to begin with, they're going to be close forever. That's the whole point here. That's the reason why I want equicontinuity of the iterates of r to the n. So in some sense, this means that 2 points in the same Fatou component, which means a connected component of f of r, behave similarly. Okay, so in some sense that's a good thing, because to understand the dynamics of the whole Fatou component, you just need to understand the dynamics of 1 point. If 1 point does something, then every other point in that component will do the same thing. Therefore, for that reason, the Fatou set is also called the region of tame dynamics. So the dynamics is not too chaotic on the Fatou set. On the other hand, the complement of the Fatou set is called the Julia set. So this is simply the Julia set, the region of chaotic dynamics. Okay, so this is where if you take 2 points that are close now, eventually they'll be far away. Eventually they'll be far away. They'll not stay close to each other. To see what these definitions really mean, let me give an example. Okay, so let's take the map. Let's take the map f of z equals z to the d, or let's say z squared really, for simplicity. So z square is a polynomial. It acts from c hat to c hat. It acts on the complex plane in the obvious way, and it takes the point at infinity to the point at infinity. All right. Now, it's quite easy to understand the dynamics of z square. So, obviously, there's a fixed point at the origin, and there's also a fixed point at infinity. Let me put the point at infinity over here. It's a no-brainer to see that any point in the unit disk, if you start with any point in the unit disk, say P, under z squared, what's going to happen? The modulus is going to be squared. The argument is going to be doubled because r e to the I theta goes to r square e to the 2 I theta. I do not care about the argument at the moment. I only care about the modulus. R becomes r squared, and if r is less than 1, then r squared is smaller than r. So the image of the point P under the map F, which is P square, is actually closer to the origin now. If P was this distance away, f of P is in fact closer to the origin. And then if you iterate this procedure, the modulus becomes r to r squared, to r to the 4, to r to the 8, and so on. So it's easy to see that the modulus shrinks to 0, and essentially the orbit of the point P converges to the fixed point 0 as the modulus shrinks to 0. On the other hand, if you start with the point Q outside the unit disk, so this is my unit circle, then what happens? The modulus increases because r is going to be r square under squaring, and if r is greater than 1, then obviously r squared is larger than r. And if you keep squaring, then the point, the orbit of the point is going to fly off to infinity. So something like that. So eventually, the orbit is going to fly off to infinity. So clearly, my unit disk exhibits some kind of a tame dynamics because all points are doing exactly the same thing. All points, if you start with 2 points that are close, eventually they will, both of them are converging to the origin. So eventually they're going to be close to each other too. And the same is true for 2 points outside. If I take 2 points outside, eventually both of them are going to converge to infinity. So in the limiting sense, they're not doing differently. Their behavior is the same. So the Fatou set in this case is exactly the union of the unit disk D and the exterior of D, the exterior of the unit circle, meaning every point with modulus greater than 1. What about the circle? Well, what happens on the circle is the following. You can pick, so the condition of being in the Fatou set was the following. If you take 2 points that are close now, they'll stay close to each other forever. But if I take a point on the circle, slightly perturb it, it will be either inside or outside. Clearly, if you're on the circle, you'll forever stay on the circle, because the square of the modulus 1 is equal to 1. So any point on the circle will remain on the circle forever, whereas any nearby point is going to either go in this direction or go in that direction. So the circle is precisely the region where the dynamics is not tame. So the Julia set here is the circle. There is a different way of understanding the dynamics of the map Z square on the Julia set, and maybe I should say at least a word or two on that, because it's intuitive. In this particular case, one can actually understand what's happening on the Julia set. So you see what I said just now is that all points in the disk converge to the origin, all points outside the disk converge to infinity. I did not tell you what happens on the circle. The circle is preserved. But what is the dynamics on the circle? Do points converge to something? Do points, is there a repelling direction, attracting? What is happening on the circle? So what's happening on the circle is the following. It's a pretty chaotic dynamics. We can take the circle, I can write it as e to the 2 pi I theta, where theta runs between, let's say, 0 and 1. Let me take 0 and 1 close. Right now, what is the so what's going to happen? So what I'm trying to say is that I can identify my S1 with, sorry, with the interval 0, 1, with identification of 0 and 1, using the argument. Now, as I apply the map z square to a certain point, e to the 2 pi I theta under the map z square goes to e to the 2 pi I 2 theta, right? So what happens to the argument? The argument theta goes to 2 theta. Now this is a simple observation. The argument of a point is going to be doubled, but this will tell us a lot about the dynamics. Why so? Because I start with any point theta, I look at its argument, I start with any point, not theta, sorry, I start with the point e to the 2 pi I. I'm sorry, did I get disconnected? Oh.
No, sir.
Okay, so can you see my my screen is, just a second. I think I have to share the screen again.
Screen is not visible.
Yeah, okay, all right, just a second. Okay. I think I... Yeah, it should be there now.
Yes, sir.
Yeah, okay, thank you. Yeah, sorry. Yeah, okay, so, right, so I start with a point e to the 2 pi I theta on the circle, look at the argument theta, and I observe that under squaring, just the argument becomes 2 theta. What that means is the following: if I write the point theta in binary, in the binary expansion, so suppose that theta is 0.a1, a2, a3, etc. in binary, then that means the point theta is of the form a1 over 2, a2 over 2 squared, plus a3 over 2 to the 3, and so on. Then what is 2 theta? Well, 2 theta, as you can clearly see, is going to give you a1 plus a2 over 2 plus a3 over 2 square, and so on. So a1 plus a2 over 2 plus a3 over 2 square, and so on. Now, this point a1 no longer plays a role because I'm eventually interested in the point e to the 2 pi I 2 theta, and the a1, a2, a3, these are all integers. So you see that e to the 2 pi I 2 theta is simply e to the 2 pi I times the whole infinite series except the first term, because e to the 2 pi I times an integer is equal to 1, so the integer doesn't play a role. So therefore, the binary, what's really happening is the following. At the level of binary expansions, under squaring, my expansion 0.a1, a2, a3, etc. goes to 0.a2, a3, a4, etc. So, in other words, I'm simply forgetting the first entry. Applying the squaring dynamics means I'm looking at the binary expansion and I'm forgetting the first entry. That's it. Now, how is that helpful in understanding the dynamics? Well, you take a circle, you take 2 points. Let's say you take this red point and this orange point. And suppose that they are pretty close. What does being close means? If they're close, then their arguments are close. Their arguments are almost equal. If their arguments are almost equal, that means their binary expansions are also almost equal. I mean, what does it mean for two numbers to be close to each other in decimal? It means that they have a lot of digits in common. The first, let's say first 100 digits are common. Same thing in binary. If 2 points are close, if the arguments of these 2 points are close, then their binary expansions have a lot of digits in common in the beginning. But as you apply the map z squared, you are simply forgetting the first entry. That means if the 2 points, the red and the orange point, if they had 100 digits in common, if the binary expansions of the arguments of these 2 points had 100 digits in common and the 101st digit were different, then applying the squaring transformation 100 times would kill everything that is in common between these 2 points. So after applying the map 100 times, the first entries will be different. And what does it mean for two binary expansions to have different different first digit? Well, one of them has to start with 0, the other has to start with 1, and then it's easy to see that that means the points eventually one of them will lie on the upper half of the circle and the other one will lie on the lower half of the circle. So no matter how close you take these 2 points, eventually they are going to be far away from each other. That's the point. That's the point. So that means the dynamics is pretty chaotic on the circle. Okay, so that's maybe so that's the definition to keep in mind. The Fatou set is the region where the dynamics is tame, and the Julia set is the region where the dynamics is chaotic. And gives rise to sort of cool pictures like these. So in all these pictures, black is the Julia set, white is the Fatou set. Questions that one tries to study for rational maps or in rational dynamics are essentially one of the sort of slew of questions, not a single question. Understand or study, let me say study, topology, measure theoretic properties of Julia sets. That means you try to understand when the Julia set is connected. It's always compact. It's a closed set, it's always compact, but it's not always connected. And if it is connected, it's not always locally connected, and so on. And there are also Julia sets of positive measure, so you want to understand which ones have positive measure, which ones have zero measure, and so on. The special case of polynomials is slightly simpler, and let me at least say a word or two on that before I try to introduce the Mandelbrot set. So what's simpler about the dynamics of polynomials? It's this, the point at infinity is an attracting point. And what do I mean? I mean the following. I take an arbitrary polynomial pz. Let's say I can make it monic. It doesn't matter. It's of degree d, so it looks like this. You can clearly see that if a point z is very large, then these guys do not dominate. The term that dominate is the z to the d term. So what happens if you take a point and apply z to the d? It goes further away from the finite part of the plane. So if you start with a point that's large enough in absolute value, then after applying the map pz, its absolute value is going to increase, and so on. It's going to increase exponentially. So that means there is an open set of points that converges to infinity. Okay. that's the reason why we get pictures like these. So here, these are all polynomial Julia sets. So you see that the Julia set is, in these cases, they are all contained in the finite part of the plane, and there is a component, there is an unbounded component outside. Like here, it's the component, the complement of the dendrite. Here, it's whatever is outside this black thing, or even here or here. Everywhere, it's just the exterior of the black object. This is the basin of infinity. It's an open set. It's not always connected. Whether or not the basin of infinity is connected has to do with the behavior of the critical points of a rational map, but maybe I won't talk about that. The fundamental question is the following. I understand what happens outside. Every point converges to infinity. What happens inside? Now, in this case, there is a way of understanding the dynamics on the Julia set from outside, but in such cases, for instance, where from the basin of infinity, you can get to the Julia set, but you cannot get to the components inside. So these are also Fatou sets, components of the Fatou set, but these points do not converge to infinity. So this requires a good understanding. So what I'm asking is, can I understand the dynamics of a polynomial, or even more generally a rational map, on its Fatou set? Because the Julia set is, as we just saw, is chaotic dynamics. So maybe it's not easy to understand the dynamics on the Julia set in general, but what about the dynamics on the Fatou set? So in this direction, so I'm going to state a couple of very strong theorems that are not easy to prove. The first one is called Sullivan's no wandering theorem. So it says that, I mean, imagine this situation. Maybe you have, you can see that there is an unbounded component of the Fatou set, which is the basin of infinity, but there are infinitely many components that are bounded. Can I have a situation where I start with a Fatou component, I start iterating the map, and I keep going from one component to another, and I never come back to the original component? Or maybe, I mean, there is no periodicity at all. Is that possible? Can there be no periodicity? Meaning, can I just hop from one component to another and keep traveling new territories along the way all the time? Like I never come back, so there is no cyclic behavior. Such an orbit would be, such a component is called a wandering component. So the opposite of a wandering component is this. So you start with a Fatou component, you go there, you go there, you go there, and eventually you come back to one of them. So this is not a wandering behavior. This is what is called a pre-periodic behavior, because you start and then you fall into a cycle. Then after some point, you are not traveling new land. You're not going to visit anything that you have not been before. You have to just move in a cycle. Wandering means that this component never comes back. I mean, it never falls in a periodic cycle. So you keep visiting new countries all the time. If that were the case, things would be harder to understand, because if you are never coming back, then how do I even understand how to study the dynamics? And I'll say why coming back is a useful thing. Okay, so the Sullivan's no wandering theorem states that the Fatou set of a rational map has no wandering component. I.e., if U is a Fatou component, then there exists some n such that f to the or r to the n of u is periodic. So no matter which Fatou component you start with, eventually you're going to fall in a periodic cycle. Now, why is this good? It's good precisely because of holomorphicity of the situation. Now imagine you start with a, so why is this good? How does this help us study the dynamics on the Fatou set? Well, you start with an arbitrary Fatou component u. You apply the map R. You go to R of u. You apply a few more times. Sullivan's no-wandering theorem tells you that at some point we are going to be periodic. Suppose that R to the third is a periodic component. Now, what does periodic means? What does periodic mean? Periodic means that there is some length n or period n such that let's say the period is 4. So you have this kind of a picture. R to the third of u goes to R to the fourth of u. Then this goes to R to the fifth of u, then R to the sixth of u, and then it comes back. So this is periodicity. When you start with u, R of u, R square of u, then once you're in R to the third, then in 4 steps you come back, and then you keep moving in this cycle. You do not do anything new. And you want to understand the dynamics of the rational map on this cycle of components. Okay, what are you going to do? So case 1, U is simply connected. Well, no, before I say that, first study the topology of U. Okay, what do I mean study the topology of U? So I do not know, I only know at this point that U is a connected set because it's a Fatou component. So by definition, it's connected. But I do not know if it is simply connected. It could be an annulus. It could be infinitely connected. It could be something like a disk minus a Cantor set. It can have infinitely many, it can have infinite connectivity. So I don't know what to expect in general. But here, what saves the day is the following. And this I'll not make too precise. So there are two options. Either just give me a second. Okay, yeah. Either U is an annulus and yeah, okay, fine. Either U is an annulus. Actually, let me be a little more motivated before stating the result. Sorry, this is just not the right order to motivate things. Okay, so let's take the simpler case. Simplest case, U is simply connected. If U is simply connected, then we have the Riemann mapping theorem at our disposal. Well, not U, but R to the third of U. I want to understand the dynamics on this cycle. So for instance, I pick this point. If R to the 3 is simply connected, what I do is the following. Here is R to the 3 of U. Here is my unit disk. There's a Riemann map well, in whichever direction. Let's say in this direction. The map R to the 4 brings R to the third of U back to itself. right? So it's r squared, r to the third, r to the fourth brings this component back to itself. So I can construct the following dynamical system on the disk. Namely, I first go by phi inverse, then apply r to the 4, and then come back by phi. So you see, this is easily seen to be a map of the unit disk, right? Because you're going by phi inverse in this direction, applying r to the 4, and you're coming back. So, and topologically, or in fact, phi is a holomorphic map. So you have not changed the conformal dynamics. The point is that this is what is called a conjugacy. So phi is being used to conjugate the dynamics to a model form. Since every simply connected domain is the disk, instead of trying to understand the dynamics on an arbitrary simply connected domain, I might as well just try to understand the dynamics on the unit disk. Because you see, iterating r to the 4 is the same on this component is the same thing as iterating this guy on the unit disk up to a complex change of coordinates. And complex change of coordinates will not change the dynamics. I mean, in one way of thinking about the conjugacy is the following: you do not think of two linear transformations. So when you have a linear transformation, you have a certain matrix representation of it. But then you know that if you change your coordinate system, then the matrix representation changes by a conjugation. But that does not change the linear transformation. So two objects, if they're conjugate, they're essentially the same. You're viewing them in different coordinates, that's all. And some coordinates might be easier than the others. And we see this in linear algebra. Sometimes if you have a matrix or a linear transformation in some coordinate looks bad, but if you can diagonalize it with respect to that particular choice of coordinates, it looks much simpler. So that's the right coordinate to work with then. Here, it turns out that this is the right coordinate. One should work on the unit disk. And why is that the case? Because of the following thing, my r to the 4 is not just a holomorphic map, but it's a proper holomorphic map because it has to send the boundary, which is the Julia set. Recall that this is a Fatou component. A component is a maximal domain of a maximal connected domain of the Fatou set. So it has to be necessarily the Julia set. And r to the 4 will send the boundary back to the boundary. So in that sense, it's a proper holomorphic map. Proper means that as you're going to the boundary in the domain, in the codomain under the map, you also go to the boundary, which is equivalent to saying that preimages of compact sets are compact. So this is a proper holomorphic map, and after conjugating, properness survives. So this is also a proper holomorphic map of the unit disk. But what are proper holomorphic maps of the unit disk? So it's a proper holomorphic map, and the proper holomorphic maps of the unit disks are Blaschke products. So these are maps of the form where all I D. So this is well, I mean, if you sort of assuming that people are familiar with this fact that every proper holomorphic map is a Blaschke product. It's a basic application of maximum modulus principle. So basically it boils down to understanding the dynamics of proper holomorphic maps on the unit disk. And here the story is not over. So I have essentially reduced the case to dynamics on the unit disk, but now I need to understand the dynamics on the unit disk. So dynamics on the unit disk is the following. This is called the Dangeau-Wolff theorem, and this is probably one of the most important theorems that allows us to classify dynamics on the Fatou set. So Dangeau-Wolff states the following: if F is a holomorphic map from D to D proper. Either F, then F is either a rotation, meaning it's conformally conjugate to a rotation. A rotation is just multiplying by some complex number of modulus 1. So it's either conformally conjugate to a rotation, or the iterates of F restricted to D converge to some point A, B, in the closure of the unit disk. And so the first case is self-explanatory. It's a rotation. The second case is slightly more complicated. It's the following. You have the unit disk. It says that the iterates of the function f converge to a single point. That means if you take any point, so there's a particular point, there's a special point P on the closure of the disk, so it may be in the interior or on the boundary, such that all points on the unit disk eventually converge to the point P. If the point P is inside, over here, this is the situation of the map Z square. Recall, for the Z square, we saw that there is a point inside the disk, so that every point is attracted to the fixed point P. But P doesn't have to be in the interior of the disk. The theorem allows for the possibility where P is on the closure. So P could be also on the boundary. So if P is over here, then the situation is that every point eventually converges to this boundary point. Every point escapes to this boundary point, and so one example of this sort, and this I'll leave as an exercise. Take the Blaschke product 3z square plus 1 over z square over 3. So you see that b of 1 is equal to 1. So 1 is a fixed point of this. So yeah, so if I try to see what this tells you, what the Naujia-Wolff theorem tells you for this particular map, so you can see that this is a map that is a proper holomorphic map. It's a Blaschke product. It preserves the unit disk, takes the circle to the circle. So this theorem applies to it and tells that either the map is a rotation, which it is not because it has higher degree. The degree is 2. Rotation cannot have degree 2. So every point eventually should converge to some point in the closure of the unit disk. So this is the situation. I have to find a point P such that the iterates converge uniformly, locally uniformly. So this is actually a local uniform convergence. Or in other words, uniform on compact sets. So, so that the iterates converge locally uniformly to some particular point P. You see that then you solve this particular, you try to find the fixed points of B, and you see that it has no fixed point inside the unit disk. So therefore, according to the Naujia-Wolff theorem, the fixed point has to be on the unit disk. Indeed, it is the point 1. So the Naujia-Wolff theorem guarantees that all points must converge to the point 1 on the boundary. Okay, so this is an example of that sort. All right, so maybe now I can complete the classification. So yeah, so let me not get into the situation where this is not a simply connected domain. That requires some tools from hyperbolic geometry. You have to use the notion of what's a Poincare metric on the unit disk. So I'll not get, yeah, that's sort of too technical for the talk. So the Sullivan's no-wandering theorem tells you that every for two components eventually periodic, and this, what I just told you, the combination of Naujia-Wolff and so on, it tells you that every periodic for two component is either the basin of attraction of an attracting or parabolic fixed point or periodic point So attracting is the situation of z squared. So this is the situation z squared. Remember, the origin was an attracting fixed point. Parabolic is this particular situation where the fixed point is not in the interior of the domain, rather on the boundary of the domain, and every point in the domain converges to that boundary point. That's the parabolic periodic point situation. Or U is conformally conjugate to the disk or some annulus call it AR such that F to the first return map. So anyway, let me state it for the fixed case. So it's easier to state. So note that if you have a component that is periodic under R to the n, instead of looking at the map R, you can simply look at the iterate R to the n. Then studying the dynamics of R is the same as the studying of the dynamics of R to the n. In fact, R and any of its iterates have the same Fatou and Julia sets. So it's enough to simply look at, so the Sullivan no-wandering theorem tells us that every Fatou component is eventually periodic. So at the end of the day, it suffices to study the dynamics of periodic Fatou components. And then once you have the periodic guys, you take a suitable iterate of the map and pass to the case when the Fatou component is fixed. So in that case, I don't even need periodic here, it's fixed. So yeah, and either every fixed Fatou component is the basin of attraction of an attracting or parabolic fixed point, or the Fatou component U is conformally the round disk or round annulus such that the dynamics of R restricted to the unit disk D, restricted to the Fatou component U, is conformally conjugate to Z going to E to the I theta Z. So it's an irrational rotation. I should say that, just a second. I should be a bit careful because I'm writing it. So this statement is about the topology of U. It's either conformally disk or annulus. And the second statement is about the dynamics. The dynamics is either an irrational rotation on a disk or an irrational rotation on an annulus. Irrational rotation means Z is going to be mapped to e to the 2 pi I theta times Z, where theta is not a rational number. Okay, so why is this important? Because, so what is the difference between theta being rational and irrational? Well, you see, if theta is a rational number of the form e to the 2 pi I times, if theta is p over q, then this map is simply e to the 2 pi I times p over q times z. And if you apply this, if you apply the map q times, you get identity. So if theta is a rational number, this is simply a finite order map. But if theta is an irrational number, it's not a finite order map, and it has more complicated dynamics. Okay, so that's the classification of dynamics of a rational map for two components, and that's more or less a complete classification. There is no complete classification of dynamics on the Julia set. That's sort of, there are lots of open questions regarding connectivity, local connectivity, measure, and so on. What is the Mandelbrot set? How does it fit into the whole this entire regime of dynamics. So the Mandelbrot set is the following. Is the set of all parameters. So it is associated to quadratic polynomials. It's the simplest non-trivial example of chaotic dynamical systems, right? So the degree of a rational map is at least 2. So you look at degree 2 to start off with. And for simplicity, instead of looking at all rational maps, you just look at quadratic polynomials. And every quadratic polynomial can be written as, after an affine change of coordinates, as z square plus c for some c. So the Mandelbrot set consists of all those parameters c for which the polynomial z square plus c has connected Julia set. Now, why is this an important thing to look at? It's an important thing to look at for the following reason. So I cannot quite motivate what's going on the Mandelbrot set, but the importance is the following. So far, we have been talking about, I should say that this is not a set that lives in a dynamical plane. This is a parameter space. In other words, all the previous pictures that we were looking at, say, these pictures, let's just say these pictures are the rational or the Newton map pictures. Those are all pictures of a single dynamical plane. You take a point, a rational map R, iterate it on the complex sphere, on the Riemann sphere, and draw the Julia and the Fatou set. The Mandelbrot set is not the dynamical plane of any map. You take the collection of all quadratic maps, and you ask, what are the points, or what are the maps z square plus c for which the corresponding Julia set is connected? And if it is connected, then it belongs to the Mandelbrot set, otherwise it doesn't. And it turns out that this condition gives you this particular set. So the point is that if you are in the interior of the Mandelbrot set, then let me say something first. So once you understand, once you have sort of a qualitative understanding of the dynamics of a single map, you ask a different question. You ask, how does the dynamics change if I change my rational map slightly? And this is a very natural question to ask in dynamical systems for the following reason. I mean, one of the motivations for looking at dynamical systems was to understand stability of solar orbits, or the whole solar system, sorry. Now, the point is, you can try to model such things, but you're never going to be able to explicitly compute the mass of something or the distance of something. So all computations are approximate. Suppose you have you did some computation and you came up with the conclusion that it is stable, but the conclusion of stability depended on your finding of distance and mass and so on, which are only approximate. So the original dynamical system that you are supposed to solve is not what you are solving. You are solving a slight perturbation of it. So the question that you ask is the following: if I have an understanding of a certain dynamical system, will the qualitative behavior of the dynamical system change drastically if I change my dynamical system slightly? And that could happen because, see, you're taking polynomial of the form z square plus c. If, say, c is 1, then you replace 1 by 1.00, so 1 plus epsilon, where epsilon is extremely small. But then you're iterating the maps infinitely many times, and the 2 points, the 2 maps can start to look very different from each other. So the question you ask is, what is the region of all possible C where the dynamics changes continuously? And it turns out that the boundary of the Mandelbrot set is precisely the region where the change is not continuous. Everywhere else, it is continuous. So in other words, if you're outside the Mandelbrot set, you take a point, you understand the dynamics, and if you slightly perturb it, the dynamics is not going to change much. Similarly, if you're in the interior of the Mandelbrot set, and if you slightly change the map, the dynamics of those two maps are going to be similar, meaning they're actually topologically conjugate. So they are more or less up to a change of coordinate, they are the same maps. But if you're on the boundary, every slight perturbation of any point on the boundary of the Mandelbrot set is going to be dynamically distinguished from the original one, dynamically different from the original dynamics. So in some sense, the Mandelbrot set is important because the boundary of the Mandelbrot set is precisely the what's called the bifurcation locus of quadratic polynomials. So this is where the dynamics is chaotic. So that's a whole different direction, understanding parameter spaces of rational maps and polynomials and so on. And there are lots of exciting questions that are open over here. Let me just conclude by mentioning another interesting direction. So the whole theory of rational dynamics. So initially we saw that one of the main reasons to look at rational dynamics was to try to solve complex polynomials. We wanted to find the roots of complex polynomials, and that led to Newton maps, and that led to general rational maps, and so on. But what about such things? So there are lots of questions in mathematical physics that lead to equations of the form, equations that are not complex analytic in nature. So you're no longer solving maybe a complex polynomial, you're solving something like Pz equals Qz bar, where P and Q are complex polynomials. Now you see, it's not easy to solve these kind of things because there is no fundamental theorem of algebra for these guys, right? So this is not I mean, if you look at the polynomial Pz minus Qz bar, that's not a complex polynomial. It's only a real analytic object. There's no easy way to see how many roots it should have, how to find the roots, and so on. In fact, this is still an open question. If I take two polynomials P and Q and assume that degree of P is different from the degree of Q, so let's say one of them is bigger, it's still not known how many roots does this polynomial have in general, whether the number of roots, and it's not fixed. So anyway, what I want to say is that, so maybe one last comment, there's a general theme in the direction of applications of complex dynamics to root finding and so on, and that is the following. Complex dynamics leads to upper bounds on real analytic upper bounds on the number of zeros or roots of certain real analytic equations. And I don't quite have time to say much about it, but if you look up on the internet, there is a note called complex dynamics. I'm not sure about the exact name, but it's something like complex dynamics and gravitational lensing. So gravitational lensing is a problem in physics that leads to solving certain real analytic equations, and you want to find an upper bound for the number of roots, and complex dynamics does give you upper bounds to such number of roots. So this is just to mention one particular direction of application. And in fact, I mean, this particular problem that I stated here, it's still open. There is no known upper bound on the number of zeros of such polynomials, of such polynomial equations. So I should have said that. A couple of books, depending on your background, if you are, so I think the easiest read would be a book by Alan Bearden, which is called Iteration of Rational Maps or Rational Functions. Yeah, this is the easiest one. And for those who have a better background on, so if you're familiar with some basic differential geometry and such things, then there's a more advanced book by John Milner. It's called Dynamics in One Complex Variable, or Complex Dynamics in One Variable. The so-called quasi-conformal maps, which is not something that you can easily study. So there's another book by, but if somebody wants to see that direction, that's there's a book by Carlson and Gamlin. It's called Complex Dynamics. So it has some modern developments. But I would say that if one wants a basic introduction, this is the most accessible book. It has a lot of examples and does proofs in complete details and so on.
Sir stated the Wolf-Denjoy's theorem. Is there any generalization of Wolf-Denjoy's theorem to bounded domains?
Yeah, sure. Okay. So non-simply connected or simply connected? So okay, let me mention that. Okay, fine. Yeah, of course. Yeah. So there is. So if U is a simply connected domain, yeah. See, the issue is that what is the problem with generalization? So Wolf theorem. So the theorem tells us that if you have a holomorphic map from the unit disk to itself, and it does not require the map to be defined on the boundary, it only requires the map to be defined on the disk, then it's either this or that. Okay. If you have an arbitrary simply connected domain, you might think that, well, I have an arbitrary simply connected domain, I uniformize it by the Riemann map, and then if you have an arbitrary, so maybe let's see what the problem is. You have an arbitrary simply connected domain U, and you have the disk, and you have a map from U to U, and you have the corresponding Riemann map here, phi. So clearly, you can talk about this map phi inverse compose F compose phi, right? So it's like going by phi, then F, and then coming back by phi inverse. And then phi inverse F phi is a self map of the unit disk. So the Gaussian-Wolf theorem does apply to that, and it tells you that the map, this guy, is either a rotation or what? Or the iterates of this map. What are the iterates of this? If you take the n-fold iterate of this, it's actually phi inverse times composed f to the n composed phi. So the n-fold iterate of this guy is converging to some point on the boundary or inside the disk. Now, there are three cases in the Gaussian-Wolf theorem, as we said. The rotation case, if this guy is a rotation, you clearly see that this is also a rotation with respect to some point. If this converges to some point in the interior, then same thing, by change of coordinate, you can say that f to the n also converges to some point in the interior. I mean, if this sequence converges to some point p, then this sequence will converge to the point phi of p. These are easy things. However, what if this sequence converges to some point p on the boundary? Note that my Riemann map phi is not defined on the boundary. There is a general problem in this direction. When does the Riemann, if the Riemann map extended continuously to the boundary, then the statement that this sequence of map converges to P would allow you to translate this information to this dynamical plane and conclude that the iterates of F will converge to the boundary point. But the problem is the Riemann map from the disk to a simply connected domain does not always extend to the boundary. And it does in one particular case. This is a theorem of Carathéodory. It says that the Riemann map phi extends continuously to the boundary if and only if this boundary is nice, namely the boundary of U is locally connected. So one direction is easy, because if P extends continuously, it will send the boundary of the circle to the boundary of the domain, and the boundary of the circle is obviously locally connected, so its image will also be locally connected. But the converse is a defect, but due to Carathéodory. Now, if the boundary is indeed locally connected, then the Riemann map extends continuously, and the convergence of this sequence of map, the iterates of this guy, to some boundary point will translate to convergence of the sequence f to the n to the corresponding boundary point. However, you do not always know that the boundary of U is connected, is locally connected. What you do then? In that case, there is a statement slightly weaker than the Donjon-Wolf theorem, but let's say DW for general simply connected domains. So why am I saying it's a weaker statement? So all the conclusions of Donjon-Wolf hold true for a general simply connected domain, provided the map F that you're looking at, this map, is defined on the closure of U. So yeah, so if you wanted to directly transfer Donjon-Wolf to this guy, to an arbitrary domain using local connectivity, using local connectivity, you can do that. But for that, you would need to know that the boundary is locally connected. If you do not know that the boundary is locally connected, then instead of looking at the niceness of the domain, you actually try to come up with a map F which does have a boundary extension. And this is actually something that is quite important in studying rational maps, because rational maps, if you look at a Fatou component, since a rational map is defined on the whole sphere, if you take a Fatou component, say U is a Fatou component, and you want to understand the dynamics of a rational map on the Fatou component U, the map is not just defined in the interior, it's also defined on the boundary. So you don't care whether the boundary or not, you can apply this general fact because the map is indeed continuously defined on the boundary. So you can find a proof of this general fact in Milner's book. Did this answer your question? Did you say something I couldn't hear, but I hope this answered your question.
Okay, sir.